Hello everyone, welcome to today's RISA webinar. This is going to cover Adapt Builder. We're going to talk today about the basics of lateral analysis and column design for frame structures for the next hour or so. My name is Spencer Lee. I'm the Senior Director of Concrete Structures at RISA, and many of you may know RISA acquired Adapt. So Adapt is now officially a product suite as part of RISA's overall company. If any of you have questions about the acquisition, you can contact us at RISA or support@risa.com. So today's webinar will be recorded. You can catch this on our YouTube channel, youtube.com/adaptsupport. If you wanted to refresh or just go ahead and send that to other users who may not be available and may have some interest. Today's webinar, we're going to talk about an existing model that's been created. We're not really going to talk necessarily about the modeling process, developing columns, beams, slabs, and so on. We're going to go right into a model, and we're going to talk about a few topics that are important in understanding for general lateral analysis in Adapt Builder. We'll talk about combinations and load generation of wind and seismic loads. We're going to talk about load cases, how load cases are considered when we introduce them into a global or multi-level model in Adapt. We'll talk about usage cases, how we can assign stiffness modifiers for those usage cases, and then also P delta. This is going to be geometric P delta, introduce combinations relevant to that analysis. And then we'll get into column design and just look at a few different types of results, drift, displacements, and go right into maybe how we designed columns, set columns up for design strips. So we're really focusing on a frame structure. This is mainly a moment frame type of a structure that we're going to be working with today. So we're going to go ahead here and get started. We're going to go into Builder, kind of introduce you to the structure here. This is an 8-story structure, and I'm going to just turn off the shading view and go right into a wireframe. I'll just toggle between the two. The floor plan changes, I believe, at level 4 in this model. This is essentially the bottom 3 floors. We have essentially a moment frame structure. There's a few walls here. We'll just consider those maybe as long columns in this particular case. They are modeled as walls, so they're going to drive some of the lateral load into those walls just based on the relative stiffness of those walls compared to the columns. If we go up the structure to level 4, we have a change in the floor plate. So we have essentially the 2 walls drop out on this side. We get a shortening on the bottom side. You'll notice at level 4, there's actually a cantilever off of this area, this row of columns. Once we go up to the next level, that row of columns drops out. So we have a little bit of variety in the frame itself. By default, all of the column to beam connections are fixed. They transfer moment. If we double click on any column, or excuse me, any beam in the structure, we can see under the releases that those releases are not made. Those can transfer both translationally and for rotation. Those are set to allow for that fixity condition at the connection. If you wanted to modify those for any particular reason, for example, at this area where we have an opening, these particular columns, we may want to release rotation there and just have a pinned condition at the ends of those beams rather. So everything here is fixed in terms of the connection. To globally modify a set of releases for a component, we may, again, I'll go back to these these beams here. I'm just going to switch this over to multi-level mode, and we're going to select those beams. I'll actually turn off the openings. Let me go to model, and we're going to go here to openings, turn that off. I can now window sweep that, and you can see if I go to a multi-story view, I've actually selected a stack of beams there because I'm working here in multi-level mode. If I want to modify those beams and their fixity, one up and coming feature is this property grid over on the left side. I'm not going to use it. It's not reflective in today's current version, but this would make these modifications quite a bit easier than having to go into the current option here, which is modify selection. And we can go over here to beams, and under releases, I'm going to release these beams for rotation on their ends. I'll just pin the beams for those particular components. Let's go ahead and talk a little bit about load generation. We're going to add some gravity load. I'll just add some basic gravity load to this and then get more into the lateral load wizards. So to add gravity load, I'm just going to select by type the slab regions, and let's go ahead and load this up using the patch load wizard. Dead load, I'll just do 15 PSF. And then for live load, we're going to use 50 PSF. Now the diaphragm in Adapt Builder specifically is a semi-rigid diaphragm. So it's really a shell element or a plate element with bending stiffness. We consider both in the formulation of the element. So if we, if we add lateral load to this, we're going to get both in-plane stress or action and also out-of-plane action. The only way to really manipulate a diaphragm so it acts maybe as a rigid diaphragm would actually be to create a usage case. And we're going to talk about usage cases and how to manipulate the stiffness of the components for usage cases. That's how you would manipulate a particular slab to act in a more rigid way in terms of just lateral translation through the slab versus any out-of-plane stiffness as well. In this case, we have beams. We may want the slab and the beam to both participate laterally to resist the lateral forces. So we're going to leave the diaphragms alone. We're going to just assume the semi-rigid behavior of those diaphragms. But I wanted to mention that in case anyone want to try to manipulate the stiffness out-of-plane or in-plane for those diaphragms, and we'll come back to usage case for that purpose. So we have lateral loads, or excuse me, gravity loads on the structure. I'll jump over here to load cases just for a moment and give a brief description of these two inputs. General loads, which we're going to ignore where it says lateral here. That's not really the lateral or the type of lateral load we're going to be discussing today. This might be more for reactions that are coming in from a timber or maybe a structural steel or a light gauge metal building on a transfer slab. If we had to add reactions for lateral load cases, that's where we would dump those here. But we're talking about more global loads in terms of building loads, wind or seismic. And anytime we use the wind wizard or the seismic wizard, those load types are actually classified as, let me pull that up. These load types here, these three, would get dumped into building loads. So if I add EQX and EQY in terms of seismic, that gets classified as a building load. If we add a general lateral load, maybe I want to apply a 100 kip load at level 7, and I go through each level and apply a story shear at that level, that can be done using the lateral load wizard. Those loads are actually proportioned to the nodes in the structure, similar to how we handle the seismic loading. So this can be set as wind or seismic. This is obviously wind. This will create external line loads on the structure that can be manipulated by the user. But any of these loads get dumped into here as building loads. Building loads are only designed for in multi-level mode. They're only considered analytically, not designed, but considered analytically in multi-level mode. So if we're working here in multi-level mode, that's the mode we're in now, this set of load cases will be solved. If we're working in single level mode, and I'll actually give you an example of that. If I say go to level 5, and maybe I have a load case 1 times wind X, that particular load combination would not even be solved. The load case would not be solved because that wind force is part of a global set of forces set as a building load case. So there's a distinction between the two, general and building. As a user, you could actually come in and just modify this, add these manually, and maybe put a set of of point loads. Maybe you want to add surface lateral loads or line loads. Any load can be added and assigned to a user-defined building load case. We just also dump these automated loads into the building load option as well. Okay, so we've added some gravity load. Let's go back to our multi-level view here. And we're going to turn off the gravity loads. We'll just set those to the side. And now we're going to go ahead and generate some loads using Wind Load Wizard and Seismic Load Wizard. So we'll do the wind load first. I'll go to Wind Load Wizard, and this input can be used to essentially generate line loads that are going to be acting on the edges of the slabs. So I'm going to produce multiple load cases. The first load case we'll introduce will be aligned with this global X direction. We're going to have wind added in the windward direction. We'll call that windward, and we'll call this leeward. The program will take this input. It will create pressures, and then those pressures ultimately get boiled down to story forces, which are then taken and distributed as line loads. So I'll show that how that happens. One thing to note that's important is this 0 degree direction follows the global positive X. If I change this to 90, that would follow the global positive Y direction. This would be what we call P90. That's the actual load case name. This would be called P0. That's the wind in the 0 case. You can see that's shown right there. If I wanted this to be reversed, and by the way, in the Y direction, this would be windward side, leeward side. If I wanted to reverse that, maybe I want this to be the windward side and the leeward side. Now the entry for the load would actually be 270 degrees, and in the other direction, this would actually be 180. Now, as a user, if you did that, you would actually be now managing 4 load cases, right, or more, depending on whether you're considering eccentricity. Or you could just do plus minus in the combinations, depending on how you want to achieve the loads. I'm going to pause here. There's a question. Let me see what the question is. Does the wind load generator handle parapet loads? The answer to that is no, it does not. You would have to calculate those and actually apply them or modify the load that the wind generator calculate. So this is mainly an enclosed structure type of a case where this generates just the main wind pressures on the building. So what we'll do is I'm going to switch this and include the orthogonal direction. So that automatically includes a low case wind P0. I'll just put in some wind speed here of 140. I'll leave the rest of the settings here alone. The exposure, we're assuming that the actual base of the structure is the exposure bottom, and then the top of the structure is the top level for the exposure height. You can see the program generates the pressures based on the different wind cases. If we want to include the torsion, we can add this. This will now introduce a load case E1, E2 is 15%. M0 and M90. So the way this works is if we look at this floor in plan, in the X direction we have some force. This is P0, and we're going to take 15% of this distance from here to here, use that as our eccentricity, and we're going to create twisting in this. So this would be M0. In the other direction, same thing. We would take that eccentricity, and this would be M90. So again, if you wanted to reverse the direction in terms of the input load cases, you could do that, but you would have to use, again, 180, 270, and then you would get M180, M270. Or we could use plus and minus in the combinations. So if you wanted to user define or modify the pressures that are going to be placed on the structure, the externally applied line loads that ultimately come from these pressures into these forces, you could come in and tweak these forces. If you go user defined, you could override any of these forces on the different levels of the structure. Once you've set up your loads in this wind load wizard, I'll apply the forces. we now get a set of line loads. This would just be as you going in and writing all these line loads in manually, which would take quite a bit of time. You could do it, use replication vertically in the structure, but this is a bit faster in terms of what it produces. There's a lot of line loads shown, so I'll immediately go and turn all of the loads off. And then I can actually boil this down to either full set of line loads, or I can go to view load settings. Maybe I want to see the wind pressures in the X direction, so the wind P0. If I now scale this back down to single level, now we get our actual line loads. So this line load, for example, is wind P0, that's the load case name. It's a building load. It's only solved for globally. And under loads, you can see the FX1, FX2 value. So this is 130 pounds per foot along this edge, and then we get the same force here. These are two separate load entries. We break it up based on the edges of slab. So wherever there's a break or a handle defining that slab polygon, we would add a separate load. But there's that force, and then over on the other side, we have the force here. Okay, so those can be edited by the user. You can manipulate them, you can delete them. They're externally applied loads, just as you would add them yourself. Those are the wind loads, and you can see those are sorted out and dumped into this building loads load case dialog. The next thing that we will add are some seismic loads. So let me go back to my global load set. I'll turn off those externally applied loads. We'll go to seismic load. This is a little bit different in how the loads are handled. Here we're just going to enter the input for the different seismic loads, and the program will create the different story shears upon the analysis. So once we say mesh and then hit analysis, the program actually calculates the story forces, and it breaks those forces into nodal loads based on the different node labels and node IDs in the structure. So we can't assign the nodal loads until we actually enumerate the different nodes in the structure. That's why this really is just input into the solver. Once you actually enter the solver, then the program calculates the forces. If you want to see what the forces are, or you want to maybe have more control over the force entry, there's a couple of ways to do that. You could go here and say user defined, and you could actually just enter the story force here. The way we proportion the load to the nodes is just based on mass, and this is the mass combination that we use. We take a proportion of each node and the connected mass to the total mass of the floor, and multiply that by the story shear. And then you could also include the eccentricity, 5%, whatever the value is. You may have to write two load cases, EQX positive and negative, to get plus and minus eccentricity in this case. So again, you could do that in the load combinations, plus and minus. That doesn't really cover all of the cases that may need to be considered for the twisting and the action that would be derived from this eccentricity or the torsion. Question: are the EQ forces calculated using equivalent load? Is dynamic analysis available? Good question. Yes, the equivalent lateral procedure is used to calculate the story forces. The program can actually handle dynamic analysis, but we don't actually design using response spectrum or any modal type of analysis. So I could go in and actually calculate the frequency and the periods for this structure to pull out those and feed those into the load generator for seismic. I could go over here to analysis. Under vibration, I could set up some different combinations to do a dynamic analysis for this global structure, set my number of modes, and then I could feed out the frequencies and periods. But beyond that, we just don't use it for any sort of design in the sense of frames or walls or just the structure in general. So as we've come on board with RISA, I think that'll change. I think some of the availability of those procedures in RISA 3D, for example, may be pushed into Adapt Builder also. But for now, this is just equivalent lateral static method for the seismic seismic analysis. Okay, let me come back over to loading, and let's call this EQX. I'm going to bump up this a little bit to 1.2. These obviously are specific to location, so I'll just use the defaults with that modification there. R factor, I'm going to say that's 4 for this model, and then we're going to set our direction and our eccentricity. Again, the user has complete control over how many load cases you want to consider in terms of direction and torsion. If you want to consider every 15-degree placement of load in that direction, you could set up, that many combinations to consider. You would then have to go in and write the load combinations for consideration of that particular load case. Here we're going to do 2 load cases. We're going to do EQX and EQY, and I'll go ahead and just apply that, and then I'll change this to, let's say, EQY, change that to 90, and I'll apply that. Now, in reality, for EQ and EQX and Y, I would probably create, let's say, EQX positive with, let's say, positive eccentricity, EQX positive with negative eccentricity, and then I would go to EQY positive, I'll call it positive, 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 negative, and then I might go EQX negative, positive, negative, negative. When I'm calling the first negative or positive is really the direction, the second negative or positive is for the entry of the eccentricity. So as a user, you may have to develop all of those load cases, and those load cases again get stored in the load case library. So these are located here. I can then use those load cases to develop combinations. Combinations is something I think that most users of ADAPT may have spent quite a bit of time with. There are ways to shorten that time. Once you've developed a set of combinations, I can import an IMP file, or I can import use it as a template file in order to bring up those combinations over and over again. In today's session, we're really going to focus on just a couple of combinations because we want to show, let's say, P delta. So for combinations, you'll notice that the default, if we go to criteria here and look at the load or the design code is currently set to ACI. So these are just basic gravity load combinations that are produced when you set the design code in the program. Because I entered the model as US units, the program auto assigns the design code to ACI 31814, and these are the load combinations. Had I set up load combos previously to this model, I could easily just import a file that has hundreds of load combinations. I'll show an example of that, but we're not going to use that. So if I go to File and I import an IMP file in, this file is actually taken from another model where we actually went in and produced all the combinations. This is called master loading ACI, and I'm going to import this file. I'll update, and I'll make sure that I don't have any components that are actually updated. So we're not updating components, we're just using this to import combinations. We'll also turn off load cases. We want to select all of the combinations. So I'll import all, select OK. This is just a warning if there's any load case or load combination duplication. Once that's done, then we can go back. Let me just come back to here. I'll go to load combos, and this basically just imported 240 combinations essentially. So this includes all of the different wind case permutations. If you look at ASC 7, for example, we have 4 main load cases. If we extrapolate those out into different directions, we might have 24 to 32 load cases. It probably depends on how the engineer interprets those. In our interpretation, we actually break this out into 32 wind cases here. And then those wind cases actually get fed into these combinations. So you can see these include dead load, live load, self-weight. If we scroll over here, let me make this dialog just a little bit bigger. Okay, you can see there's assignments for wind, And then there's also assignments here for EQ combinations. So if you go ahead and formally create a standard of combinations that you're going to use and adapt, you could use this process over and over to bring in the combinations from this master list, similar to this. One thing to note, in version 2019.1, if any of you are using that, this has changed a little bit. So if I wanted to delete a combination, or let's say change a factor, in the earlier version you had to click this a couple times to edit. In this version, if you click once, it'll allow you to edit. So that's just a user improvement, hopefully. And then also, if you want to delete a combination, you would select the load combination name here, delete. There's no requirement to double click anywhere in order to delete a combo. So there are ways to delete these a little bit faster. We're continually improving this to allow for copy paste from Excel and other areas of improvement that allow for creation of combinations more efficient than what's currently there. So I'm going to cancel that, and we'll go back over to criteria. One thing to watch out for is anytime you switch the design code, the program will actually reset those combinations. So if I go back to loading combos, those get reset. That's another thing we're working on, is just retention of the set of combos if you change the design code setting. I did that because I wanted to come back to a clean slate here. I'll actually switch it back to 14. Okay, and we're going to go in and just build a few combinations. So we'll talk a little bit about how P delta is considered. Under the analysis and design option type, we have this thing called P delta. Now this can be used for analysis purposes. It can be used for drift. The program produces amplification graphical, let's say, results for both drift and also for moment in columns when we look at P delta. And then the P delta combination can be used for design. So it can only be used for design of walls and columns. When we get into flat slabs, let's say you're designing the slab itself for combined bending and lateral action, we don't design for P delta combinations. That may change based on when this was developed, based on some feedback that we had received, in surveying clients. We felt that we could suppress that for slab design. We've since then heard from other clients that may be important to them, so we're considering adding that into the overall. When you go to floor design and design sections, allow for design of this P delta load case type or load combination type. For now, it's really applicable to columns. So, and just a general analysis results. We're going to go ahead and select, and we're going to create just a few combinations. The first combination I'm going to create, I'll just call these no code check. Okay, and these may not really reflect combinations that are required by code, but we're doing this just to really show the behavior of the P delta design type here. So first combination, I'm just going to use, actually let me create, I'll create 4 of these. Let me change this to no code check. Okay, so we're going to call this 1 times the dead load and live load. I'm going to use all service load essentially, and I'm going to now create a combination for each lateral load case: wind P0, wind P90, wind EXQ, and wind or EQX and EQY. And so we'll just replicate this. Okay, and then I'll come over here to, let's see, wind P90, and then this will be wind X, or excuse me, EQX, EQY. And so these particular combinations would reflect maybe the first order results for the lateral load set with wind and with earthquake. Okay, these are not assigned to P delta, they're assigned to no code check. And I would have more of these combinations if I was considering plus minus, twisting, combined with the normal force and so on. So we're going to call this first wind X. I'll call this one first wind Y. This name of combination cannot be the same as the load case name. So keep that in mind. That's why I'm adding the first here. So this is a first EQY. Okay, so these are, let's say, just first order results for a combination that includes those lateral load cases. The next combination is going to be called what we consider as the master combination for P delta. It's really used as the driver for generating a geometric stiffness matrix for P delta. Typically, it's not going to include lateral load. It's going to include just sustained gravity load. So I'm going to call this, I'll actually call it master PD. It's set to P delta, and we're going to go ahead here and just call this 1 times all of the load. I'll include all of the live load. That may not be true. You may just consider a portion of it if you're just basing this on the sustained load on the structure or on the columns. So this is master PD. Now what happens with this is if I replicate these combinations, and I'm going to add again 4 combos here. These will be P delta 1, 2, 3, 4. They're really just a replication of these combinations here, but now they're set to P delta. So we'll go ahead and set these up. We're going to have the same load cases assigned out here. So what happens is the program sees this master. It doesn't need to be called master. It just sees that these factors right there, 1, 1, 1, are the same as the additional P delta combinations, P delta 1 through 4. So the program now, what it does is it creates a matrix for this master combo, and it applies it to the solution of the other P delta combinations. The only difference is those now include the lateral loads, wind X, Y, and EQ X and Y. This allows the program to batch process the combinations using superposition rather than individually generating a solution for every P delta combination. You can still do that, but this is a way to get a quicker solution if your master, let's say your master combination you want to use for multiple load combinations with this transient lateral load that comes and goes on the structure. If I change this, for example, just tweak this to 1.1, and now this becomes 1.1, and so on. This is maybe 1.1. These 3 combinations here, those 3 would be solved independent. They would be isolated because they change. There's a change with this factor, and this factor. They're not applied to the same load case. However, this master, I'll do this in pink, right here, that still has the same factors as this. So therefore, this master matrix would actually be used for this combination. So you would actually have 1, 2, 3, 4 separate unique P delta solutions in essence. If I was to change that factor to 1.1. Okay, so that's how the program will process this information that you feed into the load combination generator. I'm going to change that back to 1, and we'll go ahead and just produce a solution for these combinations. Now, why do I set these up? I really just set these up in case I want to compare the results. The program will give me some level of comparison even if I didn't have these, because it has to produce a first order solution anyway, and I can see the difference when I look at amplification, for drift or moment. I can kind of see a comparison with that ratio, but this just gives me a direct comparison if I wanted to actually look at the moment values instead of having to back calculate the first order based on the amplification ratio that I get out of the results. So that's just why I set that up that way. All right, let's go ahead and talk a little bit about usage cases. So by default, the program assumes that everything is uncracked. Now, we get a question quite often, does the program actually calculate the cracking in the members, walls, and columns? And the answer to that is no. You would have to apply a modifier, a set of stiffness modifiers, just as a way to simulate the effect. Once you set up those modifiers, those are applied directly to the components that we use in the stiffness matrix, and they're adjusted for those modifiers. So we do produce cracked results for slabs and for beams, for horizontal floors. That's primarily due to just the historical nature of this program, which really, when it was first released many years ago, this was just a single level program, and we had a way to calculate the cracked deflection for just a single level slab. That still applies, but this crack deflection option does not apply to just general global analysis in the structure. So we're left with using these usage cases. To identify or create usage cases, I'll just double click on any component. And you can see under this option for stiffness modifier, there's this default usage called uncracked. Everything is set to 1. If I wanted to create additional usage cases, maybe I want to evaluate the drift under different levels of cracking, then I could edit and assign usage modifiers. I'll just create one modifier set here, or usage case. And we'll call this, I'm just going to call it cracked 50, let's say. Okay, and once I create that, I don't want to go in individually and modify these numbers. That would just take too long for anyone using the software. So I'll just define the usage case, and then I can go through and assign modifiers using groups of components. So I might select, for example, all of my columns. I'll select by type columns, and if I want to modify that group of columns, I'm having to avoid using the property grid because it's so much easier here. I could actually go here and assign the cracked modifiers right there. In the current version, I have to go to modify selection and go to column. And then here under stiffness, I can modify these. So we'll say that this is 0.5 for the bending stiffness. I'll leave the axial stiffness to 1 for this example. So we'll change that for all of the columns. If I wanted to change the modifier for beams and slabs, maybe I'll select next my beams. If I have a set of beams that I don't want to modify, then the best way to handle that would be to go here and turn off slabs, columns, walls, openings, and now I could select those beams a little easier if I'm graphically selecting them. So maybe these beams, I don't want to modify. I could go in and select control and try to select those. You can also go to different views, or a top view. It's probably the easiest way to do this. If I'm in multi-level mode, maybe I don't want to modify these beams here. I would just select that stack. You can see in multi-level mode that selects the entire set of those beams, and then I could go through and modify them. So let's just modify everything. I'll change these to 0.35. I'll use 0.35 for the slab and the beams. I don't think that's actually the ACI recommended factor for modification at strength, but I think it's 0.25 for beams and slabs. But anyway, we'll just use 0.35. We'll go now to floor design, or excuse me, to model. I'm now going to switch this over to slabs. So I can just go back to my default display, select by type again, slabs. I'm just picking each component that I want to modify. We'll come back and do slabs. Okay, and here I'll use the same as the beams, 0.35. I'll leave the axial stiffness alone. And the last thing would be the columns. I'll leave the columns as they are. So we now have a usage case cracked 50 setup that we may want to evaluate in conjunction with P delta. So if you have the need to assign different modifier sets for different analysis purposes, you could create those modifier sets. Once we get into the actual analysis of the structure, which we'll do now, we can select the combinations that we want to produce a result for and the usage case we want to apply to that result. So let's go ahead and do that. I'm going to mesh the structure first. I'm in multi-level modes. We'll mesh the entire structure. Now there's a few settings here for meshing that are important. My walls do not have any openings in them. So if I come back out of that just for a moment, let me go to this wall, for example. You could actually assign and define openings in walls. So if I create an opening here, there's a dialog that lets you create openings in these walls. You could copy that wall up, have the same stack of openings. Maybe it's for an elevator shaft. If your walls are solid, then the meshing that you might use would be, let's say, it's just simplified. Wall openings are disregarded when we use simplified. So even if the wall opening was modeled, we would ignore it. We would just mesh through it and assume it's a solid wall. If you want the opening considered, you would actually go over to the advanced mesher, and then you could input different sizes for the horizontal elements, the slabs, and also the walls. And these could be set to spare, so uniform meshing. So this would allow meshing around openings with consideration of the opening and the analysis. This just ignores it. There's two different approaches there for analysis. We'll use the simplified method, and I'll just mesh the entire structure here. Okay, we're going to run the analysis. We'll look at a few different results as it relates to drift and maybe P delta, and then we're going to go into, let's talk about column design. We may need to design both columns and also strips for actions along these frame lines with the moment beams, let's say, or the moment frame beams. So we're going to analyze this structure for our entire set of combinations. Notice this is just a warning saying that these load cases are not assigned to any load combinations. That's okay. We didn't do that, so we'll just say yes. Now I can assign the set of combinations that I want to run the analysis for. So we have our default set of combos. I'm not going to run initial. That's more for pre-stressing. This is just RC for now. We don't have any post-tensioning. I'll go ahead and select the usage case. I want to run this with cracked 50, for example. And we'll go ahead and run the analysis for that set of combos. This should just take a moment to run. The more, obviously, the more nodes you have, the longer the program would take to run, and also the number of combinations. There's definitely different things that could produce the need to, for time in order to get through the analysis. If I introduced, for example, a foundation, maybe a mat slab with springs, and I want to analyze this for that foundation system, then that takes longer if we consider the springs. So there are things that would build on each other that could potentially blow up the analysis time. So this is done running. The first thing I wanted to show is just graphically some of the results here for P delta. So once you run P delta combinations in the program, under loads, we actually have a categorization of P delta. Master P delta, and then these are the ones that include the lateral load cases. If I just select, this is wind X plus the gravity load, and I'm going to go to columns only, come over here to analysis, and under drift, you'll notice that I have an option here to check drift based on color coding. And so, and this also gives you the value, but what's happening is it's checking against this setting here, maximum allowable drift. This might be the required drift for seismic consideration. Maybe it's 0.025, and we would include the amplification factor in this value. So the total percentage allowed here is 0.5%. This would be including, again, the built-in C sub D value for amplification if that's required. And so we can set our maximum allowable drift as a percentage, If I come back here, let me check a earthquake. This is P delta 3. This includes, I think, EQX. So if I come back here to drift combined, this is the combined drift for both directions. This is really just the global drift value compared against that allowable. You can see the maximum is 0.54, which exceeds that 0.5%. And if we look at some of these values specifically for this combination, we can pull out exactly where we exceed that number. I could go into drift X. This again includes EQX. We would expect that that's driving this number here. Or I could go to Y separately. In the Y direction, under this particular combination, the drift is quite small. So there's nothing going on there. In terms of amplification, if I take the second order to first order drift values and look at the amplification, there's really just a 1% amplified drift here between those two values under combined. So the program would check that. This particular graphical check being amplification factor is checked against a maximum allowable of 1.4, which would give some indication of the stability of the structure, whether that meets that stability threshold. So if you go over to display, you can modify the moment amplification allowable and the drift amplification max allowable here. That's code checked against that number. And so this gives you that amplification for drift. Looking at the drift values for P delta in the X direction or Y direction, again, this is actually the drift percentage. This is amplification between second and first order drift. So there's two different options there for looking at drift. Now, if I wanted to see the first order drift, obviously I would come back here. Remember, I set up the no code check. This is really the first order number. Now, this is set to no code check. So graphically, there's nothing there in terms of amplification because this is not a P delta combination. So the program sorts that, says it's not applied or not applicable, but I can still check drift. So combined drift for the P delta combination using the same load cases, we are, I think, around 0.5, and in this case it's 0.03, 0.03. If I come back and just toggle that back to, actually I'm looking at the wrong case, this is wind. So this is 0.51, 0.5, 0.51 for first order. If I switch that to P delta 3, which is EQX, these jump up slightly. That went from 0.51 to 0.52. So there's a slight increase. That's also shown in the amplification that we saw earlier. Another graphical result that we can check using this output here would be moment amplification. So we'll jump over here to actions under moments. Let me check P delta. Let's do that EQX again. Okay, so we have moment amplification factors about R and about S. The default orientation here, this is R, this is S. So if we're looking at load in this direction, we're mainly looking at primary bending about S, let's say. And so we'll go to the S direction. This shows a maximum amplification of 1.08 between the second order moments and the first order moments based on this P delta load combination. This is again with EQX. And we could use this information again to check severity of that amplified moment due to the P delta effect. This is for big P delta, not for little P delta or local member P delta. So material nonlinearity, let's say. So those are just a couple of ways we can use the P delta combinations in terms of code checking and graphically looking at results for drift and moment. Now these moments that are amplified can then be used for column design, and we'll show that here in a moment. Back to drift, there's an additional set of results that you can tap into for drift. If we go over to reports, analysis data, drift report. Now I can produce a report based on any set of combinations I select in this dialog. So if I just boil this down to P delta 3, maybe I'll do first EQX and P delta 3. So these two kind of correlate. One is first, one is second. Now I can use this set of settings. These really tie back to the graphical settings that we had set earlier, but you can manipulate them in graphical format or here in tabular format. We'll select OK, and the program will launch this file, which shows quite a bit of information. So this will list the columns top down. This is from plane 8 downward, all of the columns, the coordinates. So this just gives indication of where the column might be located. And then we get into the displacements. These are the raw deflections based on the analysis. So you can see at this column between first and P delta, you get 3.63, 3.66. This is the X displacement, Y displacement, and combined. And you can go through any set of combinations to produce that data. We show drifted columns for both selected load cases. Or load combos, drift in the X, Y combined. This is really just a reflection of what you may have seen graphically. You can see right here, these are the no good column positions in the model. So these values for combined drift just exceed code or exceed the threshold that we set in the input prior to entering the Excel file. Average drift, this really takes the average of all columns in the same floor. So we have 2 entries per floor, plane 8 down through plane 2. 2 entries because there are 2 combinations that we're looking at, but this is the average of all column drifts. This really is the average of all column displacements in the X, Y, and combined direction. And then we get the average of all column drifts for this combination in, again, the same directions, with a code check. So if we look at maximum drift, this envelopes the combination selected. So this is really enveloping the first order, second order for EQX. Again, shows the plane, and this just pulls out the maximum drift for any of the 2 combinations that we've produced the result for. Average drift envelope. This is a similar type of result. It's enveloping the 2 combinations and just producing the average drift for the enveloped condition. And then finally, we get amplification for the P delta only combinations for each column. So for P delta 3, that was one of the combinations we had selected. We're looking at X, Y, and combined drift, and our amplification threshold is shown there. So this information can be useful if you're trying to find displacements, amplified or not, for different columns in the structure. And that was introduced in version 2019.0 of the software. So in the remaining few minutes that we have here today, we're going to now look at just an example of designing a column for the amplified actions due to P delta, and maybe looking at the design strip results for a moment frame, for example, in this model. We'll start here with the design results for a strip. So I'm going to go back to my default display. I'll go to level, let's go up here to level 7. And this would need to be carried out for all levels that you wanted to design. But in this case, what I need to do is I need to develop design strips in the floor. And in this example, I'm just going to isolate this one frame line here with these beams. I'll go ahead to floor design. I'm going to create a design strip along this path. Okay, and we're going to say that this support line, if I double click on that support line, I want to change that design to beam design. If I go to beam design, I can now decide whether or not for the actions that are going to be produced along the design cuts, do I want to design those using the effective width of the beam slab, or do I want to use the full tributary? The program, when I generate this strip, let me go ahead and do that. I'll use a splitter Usually I would not be using the splitter because I would put strips on all frame lines. In this case, I'm isolating just one. So we'll use a strip. I'll go from midpoint of this slab region over, and I'll just cut that straight across. I'll generate the design cuts. And again, the program will integrate over this path of the design cut to produce the actions for this section. When it comes to the design of this beam line of this section, I could then design it based on the reduced set of properties for the effective width of the slab, or excuse me, the effective width of the beam if we use effective width here. So I'll use effective width on that strip. Once I set that strip up, I've already produced a result for my different design combinations. I could go through now and just design those sections. Once I design the sections, I would then be able to produce reinforcement for these design cuts. Now, one thing I want to mention here is, remember, we created combinations that were really associated with some gravity, service, and strength. This is non-lateral. Initial, that would require the presence of post-tensioning, so that shouldn't produce any reinforcement for us. No code check. The program is not designing for these, and it's also not designing for P delta. So it's really only designing for gravity loads in this case. If I change these load cases to strength, then I would actually get a design for the presence of the lateral load effect for first wind, first Y, EQX, and EQY. And so if we needed to include those combinations for the design of these frame lines, then we have to build out additional combinations in this example. I could produce results for those combinations. For example, if I go to first EQX and I go to bending diagrams for these design sections, this is my bending diagram for that frame line. And if we go to the numerical display under floor design, I can see I have, kind of a classical shape. There's a little bit of curvature on the shape due to the gravity bending combined with the lateral. But these ultimately are my actions on that strip. Unfortunately, they're not actually being designed for because this is set to no code check. If I wanted to design for it, it would have to be set to strength to design for these moments. So what the program is actually designing reinforcement for in this frame line currently is the strength combination here, these gravity and these service. This would produce minimum reinforcement. So if I switch this to strength dead and live, you get a different diagram shape. This is really what the reinforcement is produced for. If I calculate the rebar for this beam line, you can see the reinforcement here for the beam. So this reinforcement can be produced different ways. I can produce it as actual bars in the plan, or I could go back and under analysis, let me collapse that. We'll go over here to design cuts, reinforcement. I could produce a calculated display of reinforcement. So this gives me a numerical area of steel along the strip for this combination. If I went to envelope, this is my enveloped required area of steel. If I wanted to see what was actually provided by the program, now I have to calculate the reinforcement. I've already calculated the envelope of reinforcement, so this is really what program has provided for this beam. Green is top rebar, blue is bottom. But you could do this for an entire slab, multiple support lines, and so on. The last thing I'll show here is going back to the effective flange. You can see that this physical cut is 180 inches wide. Be effective it's using is actually 86 inches wide. This is the idealized cut and the member that we're designing the reinforcement for. So that would indicate that effective width that it's using when we actually process and design the reinforcement. The last thing we'll show, we talked about columns. So we're going to go back to our column design quickly. And these columns basically are not set to a section type. So if I wanted to design this stack of columns here, and I'm going to assume that the same amount of reinforcement is required for the stack, even though that likely is not true. We want to probably vary the bars to economize the design. But I'll just select that stack and say, I want to design that stack for the same design section, the same level of reinforcement in the section. So I'll go and I'll modify that stack. I'll create a design group for it. We'll go ahead and auto assign a new group. And then I'm going to go over to column design and define the reinforcement in that group. The group is called a 36 by 18. I could override that, but that is basically this column stack here. We would set up some properties for this design, and let's go ahead and set this to vertical bar size. I'm going to use, let's use number 9s. For face bars, I'm going to use 4, and for end bars, I'll use 3. Gives us 1.5% row. We'll say we're going to use number 4 ties, and we'll do 12 inches on center. Then you have some other settings here that define the way that ties are considered when we go and process this particular column stack. So once I've defined my column group, this is a column group of 5 or 6 columns. That column group will be checked against the section type that we've defined. I'll go under design settings and I can set up the different parameters for the design. So I only want to design maybe for these P delta load cases. I'm going to use the finite element results. That's my force source. And we ran it globally. So I'm going to use global analysis as the governing analysis. We don't have any post-tensioning, so hyperstatic, this doesn't really matter. We have a few other settings here for the design of the column. We'll just select those combinations again. Once I've done that, now I can actually code check the columns. So I'll code check for the P delta. This is 7 columns. We'll code check. I'm code checking versus designing. If I design, the program will just determine, number 1, does the current rebar work, and if it does not, produce an alternate design, increase the number of bars, maybe even decrease the number of bars to meet the design for these columns. Now, I usually like to code check to see if my defined section works. So once I design that, now I can go in under the option for columns. Let me collapse this. And code check results are actually done under this individual column design result. So we have some warnings here. There's a status check. There's one column doesn't work. A couple are acceptable. The rest have warnings. I mean, that tells us a little bit of information, but probably not enough. I might want to see the utilization for the columns. So if I go to V&T utilization, and the display here is set to value under components, this is value versus status. Okay, that's important if you want to see the numerical numbers on the display. Now I can go in and say, okay, I have 17% over stress when I look at the shear torsion utilization in this column here. This is actually the column that I think was giving us issues with the drift also. So that probably makes sense in terms of the relative comparison of the result. And if you wanted to go dive deeper into the results for individual columns, now I could select a column, maybe go and check the design summary for that column. This will open an HTML file. And if we roll down here to the bottom, we have a couple of warnings. This shows message 4, message 8. So shear and torsion exceeds maximum, the utilization is greater than 1, and then the spacing here exceeds allowable for the shear reinforcement. So we could go through and now what I could do is actually take that column. I may not want to design the rest of my columns because they may actually be okay. I may have to separate and kind of segregate this column out from the rest to design it. So for this column, I might go in and actually create a new design section type. So I'd create a new type, call the name of that particular section, designate that type to this column. I just segregated that although I also changed the size there. And then I would actually design that column versus code check. So there's a process for grouping the columns, assigning the initial sections and the reinforcement, and then going through the code check of the members. All right, we're going to go ahead and stop there for today. I'll just leave the last 5 minutes or so here for any questions that anyone has. If you do have questions outside of the meeting, you're always welcome to contact us. You can contact support@adaptsoft.com or support@risa.com. Likely that will change to the RISA support in the next month or so, but currently you can send emails to either of those addresses. So thank you for attending. I appreciate it. This video will be put up on our YouTube channel, and go ahead, and if you have questions, you can type those in. I'll wait just a few minutes to see if there are any. Thank you. The question is there a way to do small p delta? The answer is no, not at this time. That's a short answer. Let me just see. The question is like creating small columns with intermediate nodes. And you could manipulate the program to determine, if you had intermediate nodes, you actually don't have to create a small column. You could discretize the column differently. So Marcus, if you actually went into the, there's a file, I'll show this here. Let me escape out of that. And there's a initialization file. If we go over to Windows, this is kind of buried in the program files. But if you go into the builder program files and you go into the initialization file for this program, whatever version you're on, there's an option here to create divisions. So the vertical division for a wall is 2 divisions for shell elements, and the column division is 2. So if you create multiple divisions, then a particular column, right now this column is actually discretized into a frame here where you have a node 1, 2, and 3. If I said that was 5, this would actually be broken up into multiple nodes. So you could get displacements at all 5 of those nodes, for example. If you had to create a restraint at a node, then this would not work because I can't really create a restraint at this node without having a reference plane there. So there you would have to create the 5 different levels, and then you might have to apply, some sort of restraint or support at the node. It could be a spring, it could be a pin, fixed support, whatever you require to simulate the need for the small p delta. All right, well, we'll go ahead and end there. Thanks again for everyone joining today, and let us know if you have any questions. Thank you.